Testing, testing. All right. So we're going to have a panel, and we're going to talk about infrastructure for AI agents. We've got a great panel, people working across the infrastructure stack who've done a lot of interesting work. And I think we're going to kind of start off our session, and we're going to try to hear from the panelists what they think is unique about this agentic era, and why it's even an interesting question in the first place to talk about infrastructure for AI agents. You know, what's new? What about this regime is different? So maybe we'll go ahead and query a couple of the panelists and see what they think. We'll start with Igor.
Hello, can you hear me? Turn it on. Can you hear me? Hello, can you guys hear me? Okay. So first of all, great privilege to be here with distinguished panelists here. What's different about agentic AI from the infrastructure perspective? What we see agentic AI doing is, one, generating a lot more tokens than just non-agentic AI. It typically requires very long contexts. Think about coding agents, things like that. And what it also requires is very low latency and very low cost. Imagining you're kind of constantly querying the model, so you don't want to sit and wait 10 to 15 minutes for your deep research query at OpenAI to complete. You want to do this really quickly so you can actually get more results and then iterate again and again. I never got an intro to kind of give on Groq, so maybe I'll take like 1 minute. We kind of meet all these requirements as a hardware. Groq started as a software first, inference first hardware startup at about 2016. And our focus from that point on has been maniacally focused on inference. And the resultant of that has been an architecture that's vertically optimized, from silicon, custom silicon, to custom networking, to custom kind of software stack that allows us to run very low latencies, best of breed latencies, very low cost. And we've been able to do this. We've been able to do this with a 10-year-old technology. So Bill kind of listed a number of requirements for agentic AI: high memory bandwidth, a lot of model parallelism capability. And we have actually built this system. We have it available now. It's kind of setting records on performance, and we're deploying it across the world. We have data centers here in the US, in Canada, in Europe, Middle East. About 1.8 million developers working on this. And really, we're kind of embracing all the requirements for agentic AI. Thanks.
If I may, I'm just going to add, it's also, what's also specific about the agentic AI infrastructure is that it's full spectrum, as I said, from edge to endpoint to cloud. And it comes actually with different requirements for the hardware. Like on laptop, you want to go as low power as possible because battery life is important. In cars, you want to go as low latency as possible because if your self-driving car detects a kid jumping on the road, you want to brake rather in nanoseconds than in seconds. And in data center, it's all about compute power, a lot of memory, a lot of memory bandwidth. And also, it's fully connected. All these devices are talking to each other. They actually can discover each other, either they're in the same vicinity or not. So those are the big differences with what we've seen with the internet boom and the cell phone app boom and so on.
Yeah, well, I think most of this has been said. I think there's unique needs in terms of quality, quantity, and system issues. I mean, it's going to be a lot more tokens because you're working through this hierarchy of agents. They're going each through chain of thought. The quality is going to need a lot more bandwidth, a lot lower latency than what we're used to, and also a lot of resilience. We typically will build these systems across many GPUs, and we have to have everything operating all the time. And then these agents are querying tools, and a lot of the tools involve making queries to data lakes of different kinds, databases of various kinds. And so you need to have storage integrated in these systems in a very seamless way for them to do that as well.
Yes, I just want to double click on inference. It feels like data becomes an old field, and inference is the engine to generate new field. And literally, I see a lot of people sort of like training small models on a local laptop while making a lot of external API calls with bigger models trying to get these word functions. So it feels like there might be an economic shift from used to be doing research is like the cost of labeling data plus cost of training. Now it's the cost of calling inference API for model verification plus fine tuning. So that's a lot of opportunity for inference.
Yeah, maybe a couple of things that I'll add. I'm both moderator and panelist, so I'll throw in some. Yeah, very unfair, exactly. Yeah, maybe, and one thing I'll add is, I think there's a pretty unique distinction. There's kind of almost two regimes within agentic infrastructure. One is the very low latency, very performance sensitive regime, right, where you're asking a question and you're bottlenecked by a long agentic graph unfolding, and so you want each step to be as efficient as possible, and you care about latency most. And then there's also to a more extreme degree than I think has been typical, at least in AI, that async batch offline regime, where you might want to, for example, send off a query that runs throughout the night. Maybe you have a Codex agent or something that's doing work for you asynchronously and just checking your code base when you're not working on it and can run overnight. And maybe you're spinning up many, many of these. And so it's actually this kind of unique, kind of two different regimes, almost probably kind of two phases. And building infrastructure that handles both well, or kind of splitting work across them, doing kind of indexing work, but then also serving work. I think that's in some ways a classic problem, but I think it looks a bit new in this new context. Okay, very, very interesting. So maybe on that point, actually, the next question is about what are some of the things that are stable in time that aren't changing? In what ways is history rhyming in this agentic infrastructure? I think, obviously we've been through a lot of phases of computing. Yeah, I'm curious what people think. Maybe we'll start from this side this time.
Okay, so because Lambda is like cloud, so I think operational efficiency is very important. We'll stay here for a long time. Just imagine a world where AI is going to consume most of the compute. And it's very important to effectively distribute those compute for different use cases, training, inference, agentic applications, and also making sure whoever has a compute can basically use them very efficiently. It reminds me about like early days of cloud computing. You have like virtualization is a great breakthrough. I guess the technique will change, the use case will change, but underlying principle of elastic provisioning, load balancing, those things will stay for a long time.
Yeah, well, I think what people really care about is that they have a problem to solve, that they can solve it quickly and adapt quickly as their customers' needs change. And to me, there are two ingredients to this that I guess things have always been pretty consistent. One is programmability. You need to have a good, solid programming language that things are built on top of, like CUDA. And then you want to have frameworks and libraries so that when you want to prototype something, you're not starting from scratch. You can take something that's mostly there and kind of customize it and plug it together and get your solution very quickly. And I think that's something that's been persistent across many generations of technology.
I think in general, something that's consistent with each era is that the battle is won basically on three axes. One is TCO, total cost of ownership. It includes efficiency and all that. One is dependability, which includes safety, security, reliability, and so on. And the other one is user experience, as Bill was saying. And those are the same axes, but at each evolution of technology, the means to get there are different. For example, cooling, liquid cooling, and chipletization, for example, is one way to get to cheaper cost and better TCO. And open source software improves both TCO and user experience and so on. But the axes are basically the same as during the previous few technology booms.
Yeah, I agree with Bill. I think user experience is going to be key. How quickly can you deploy your workloads onto the hardware? So that's key. I think the other piece is really efficiency. As we know that power performance area is really important for CPUs and so on, but as you scale hardware at a much massive scale, this is going to become even more critical. So just like we've optimized mobile processors so our batteries last a long time, I think we're going to be driving that level of efficiency on inference hardware because we're just going to be generating so many tokens, so many calculations need to be made. So that's kind of key.
Yeah, very interesting points. Yeah, I think the one thing that's becoming clear hearing your answers is there's always a question of, is this time different, or are some problems classic and repeating? And I think there was a period, probably even just a year ago, when in AI the broad consensus was that we would just do kind of pre-training, scaling. That was going to be the only regime, and then we'd be inferencing these kind of monoliths, and that would be it. I think it's becoming clear that now there is going to be a heterogeneity of workloads, a great variegation of workloads, different types of training workloads, post-training, pre-training, inference time scaling, types of training, et cetera, and then also very different types of inference workloads with different SLA profiles, et cetera. And that's a classic problem that systems people have been wrangling with for a long time. So interesting to hear that this time is not different in some ways, while being very different in others. Yeah, going forward to another question, I guess the next question, maybe two questions in one, take it as you will. One is, what are things that the consensus is getting wrong? Ideas and perspectives and opinions you hear a lot from colleagues in the industry, from Wall Street, or the media, et cetera, that you think are misguided. What are problems that are getting too much attention, problems that aren't getting enough attention? That kind of, what are people wrong about? Where do you have a different perspective that's a bit divergent? Maybe we'll start inside out this time.
Okay. So to be maybe a little contrarian, the fact that the new compute is now only GPUs and CPUs are dead. CPUs are actually re-emerging. So GPUs definitely are exploding, but they're making actually CPUs re-emerge, especially with agentic AI calling tools. Those tools are mostly on CPUs. The other thing is what you mentioned about pre-training. Actually, the explosive era of pre-training is probably slowing down, and we're running out of data anyways for text, for video images, it's another story. But what is really scaling right now is post-training, especially with RL for verifiable domain, as well as inference with generative inference, which obviously generates an awful lot of token with tree of thought and so on.
Igor.
Yeah, so I think one of the biggest misconceptions that I find is that the belief that what the infrastructure that got us to this point is the same infrastructure that's going to take us forward. So if you look at most of the focus up until now has been training, and we've built really good training hardware. GPUs are unbeatable on this, and they're going to continue to do really, really well. Inference is a whole different beast, right? You're not processing high batch. You're not running it once. Like if you look at the hardware needed for inference, it's about 20x than the hardware needed for training. So the efficiency of that hardware needs to be significantly better. The latencies, as I mentioned earlier, need to be better. Real-time processing is key. And this is very different hardware. So I think thinking that we're just going to scale more GPUs for inference, I don't think that's going to happen going forward. I think it's going to be a very unique custom designs that need to be brought up.
What do you think about that, Bill?
Yeah, so GPUs today are the most efficient and most commonplace platform for inference. They do a really, really good and really efficient job of inference, and they've been optimized for that. We actually optimize for distinct workloads. We do optimize for training. We also optimize for inference, and I think going forward, they're going to be quite good at that. I think the one big sort of error in conventional wisdom that I see is not using GPUs for inference. It's focus on large models, and I sort of understand why people do it. Everybody's worried about their flagship model, but especially as we move to agentic systems, what I see happening is people distilling the really big models into smaller models that are then specialized for their particular task in the agentic system. And I think there's going to be much more concern with running an 8 billion or even a 1 billion parameter model really efficiently than running some behemoth trillion parameter model, especially as we move toward mixture of experts. And this is actually one way of doing mixture of experts, kind of at the level of individual agents. You have agents with just the knowledge they need.
Very insightful. Yeah. Fine.
And so just to get myself out of the debate here, I'm going to talk about eval. So I think eval is something both over-indexed and underutilized. The problem here is the disconnection between leaderboard eval with the real-world problem at your hand. Again, I'm going to make a connection between eval and recruiting. Just imagine, like you are looking at someone's resume. What the person did at school in terms of course and scores are sort of important in the early stage of career, but it gradually become irrelevant. What I really care about is what they did in the past in terms of project, what they built, and how that is going to help you with your task at hand. So really, it's going to be embody the eval and the continuous development.
Case in point, Llama 4 was #1 at all the evals.
Yeah.
All right, I'm going to dodge that. Awesome. Yeah, it's very interesting. Yeah, I like a lot of these points. Yeah, Bill, I think your point's particularly thought-provoking. Yeah, among several things, I think one of the misconceptions that I'd like to combat a little bit is the idea that basic research is dead, that it's all engineering from here on out, that we've answered all of the questions, we just need to scale things up. Yeah, claps for basic research. All right, awesome. Yeah, a couple of claps there. Yeah, I think that as one case study, the recent Gemini DeepThink model gets kind of a greater lift from parallel thinking than it seems like some other models have gotten. And I think there's a lot of evidence that composing these models, you can get kind of much better results. And so you've started to see academic labs doing work at this kind of inference level of the hierarchy. And I think there's a lot of gains to be had there. Like the differences in the way that you construct these ensembles, the type of aggregation functions, it can make a big difference. And so I think we're going to start to see, hopefully, the pendulum swing back. And there'll be a lot of room for novel research ideas, just like in the kind of 2010s and neural networks here. So I'd encourage people to, kind of aim for the frontier. Awesome. Okay, so with that, actually, that's a nice segue to a last question here. We have like 3 minutes or so left. I'd love to talk to the panelists about what is your advice for graduate students, researchers, and people in the audience who are trying to push on the frontier, who kind of want to make things better, even at either at the infrastructure level, at the applications level, or kind of the models level. Any advice for people? Maybe starting with Bill.
Yeah, so my advice is to reject conventional wisdom and try to think about how good things could be. Try to come up with a physical argument for bounding what level of performance you could achieve, what results you could get, whether it's out of an agentic system or a piece of hardware. And then start from first principles and look at that. Too many people are kind of doing incremental things, taking the conventional wisdom and trying to push it another notch forward. And the real big leaps happen when somebody tosses that aside and starts from first principles and says, well, here's how good it could be, and then pursues that.
Chun.
Work on small models, try to make them big models. It's just very cool in multiple ways.
Ramin.
My advice is be a full stack scientist or engineer, meaning it's good to specialize in something. Like if you want to specialize in AI architecture, that's great. But be full stack. Understand the hardware. Understand the communication issues. Understand the model. Understand the application level. Because that's what I've seen throughout my career. The best outstanding engineers are full stack engineers. They're never people who know everything about one thing. They're people who know nothing about everything.
Very interesting. Igor.
Yeah, I'm going to echo Ramin's comments there. Yeah, I like foundational science. Focus on that. I like breadth of understanding. I think this is a big challenge also. If you look at our infrastructure, everybody's focused on the chip, but nobody has looked at how do you deliver power? What's the loss of that power delivered? How do you thermally cool these things? How do you pack racks? And that is really maybe less sexy than kind of getting TOPS per watt out of a chip, but it is super important in our data center. So just this broad understanding of how the whole stack is built, and maybe you can then focus on in depth on a component, but just get your broad understanding of how everything clicks together.
Yeah, I'll actually have to third that opinion. Yeah, I think driving a nail through, focusing vertically is really important. Kind of not constructing arbitrary boundaries around what is in your domain versus not. I don't think people appreciate the extent to which infrastructure has shaped research, the extent to which the transformer co-evolved with the TPU pod. and isn't really necessarily a smart thing to do versus the LSTM, but it makes a lot of sense if kind of memory bandwidth is a constraint and compute is very, very you have dense computation systems. So. Yeah.
And if I may, just to give a concrete example, the reason I say the most outstanding engineers are full stack is because they're the only one who can debug a problem. Because when there is a problem, you don't know if it's in the model, it's in the software, it's in the hardware, it's in the communication. And if you're specialized in one thing, you just won't understand the problem. People who are full stack, whether it's software, hardware, model, communication, anything, they just figure it out.
Yeah, really, really great point to end on. Thanks for a very, very fun panel. I learned a lot. Thanks, everyone.
Thank you.
Thank you.